All right, yeah, you can start. Thank you.
Hello, everyone. My name is Ashmal Vayani, and I study Masters in Computer Vision at University of Central Florida. Our talk today is going to focus on building multilingual and multicultural aware multimodal AI systems. So the title is "Speaking the World as Seeing the World as It Speaks: Multilingual, Culturally Aware Multimodal AI." The central idea of one-liner about the talk is that AI should not just understand language, but it should also understand the culture that shapes the meaning across the world. To start with, let's see how this generative AI has revolutionized how we communicate with the models, such as ChatGPT, Gemini, and Anthropic, which is cloud. As we can see that these models can interact with humans. They can generate text and images with human-like fluency. But these systems are mostly trained on high-resource languages like English or Chinese. That means they often fail to capture cultural nuances and underrepresent millions of global speakers. Although these models are pretty good, but they are bad on certain aspects, such as they focus on high-resource languages. Most of them are pretty close source, even if they're good, and then they overlook the cultural richness of the lower-source languages, and they don't perform well in the multilingual settings, which we show in the future slides. So the goal of our research objectives were to have a culturally aware multilingual image, large multimodal model benchmark, and then followed by video large multimodal benchmark that we will be talking about in the talk today. So now let's start with this image large multimodal benchmark. So the first paper we are going to be talking about is All Languages Matter, Evaluating Large Multimodal Models on Culturally Aware 100 Languages. This paper was accepted at CPR 2025. It was a highlight paper we presented in Nashville earlier this year. And this was a joint collaboration with Mohammed bin Zayed University of AI and UCF. So the motivation behind starting this project is, as we know that existing benchmarks, they focus on a couple of highly sourced languages. They overlook cultural richness of the lower source language. They lack diverse question types, and they don't test cultural knowledge very well. They are often unfair. That means they're limited to a single question types only. In most cases, it's just a multiple choice questions. So the motivation is to create natively verified, multilingual, and culturally grounded evaluation datasets so that inclusivity becomes measurable. ALM-Bench fills this gap. This is a global visual cultural benchmark for over 100 languages, and it comprises of several categories and domains. As you can see in this image, it has several question types, and that's humanly verified. More vividly, our benchmark comprises of 4 question types, including log questions, true, false, short questions, and multiple choice from different parts of the world in different languages. We compare our work with the existing works, and as you can see, the existing benchmarks have several limitations. Most of them are mostly monolingual. That means they're limited to being an English, Chinese, or Arabic benchmark as their only primary language. These domains and the question types on them are also pretty limited. They're either limited to short questions or large questions, or multiple choice questions only. And the domains or question types, they're usually smaller. They don't target very large number of domains, and they don't capture this cultural semantic contents. Some of the recent works, like CVQA paper, that does consist of multilingual data. However, they're also limited to multiple choice questions only. To contrast, we present this ALM-Bench, which comprises of 100 languages, which is 3 times more than the recent works. It contains more domains than the humanly verified samples, and we completely open source our data set in the data curation pipeline. To formally introduce, this is the first of its kind multimodal benchmark that comprises of 100 languages, and then equal proportion of low resource language versus high resource language. It was captured and curated with over 800 hours of human annotators, which were pretty expert in their cultural domain and their native languages. It contains 3 times more languages than any nearest recent work, and double the image domains and the number of samples it had. And then we also evaluate several large multimodal models, state of the art, and we showed there's several several shortcomings on them where they struggle in the lower source languages or the multicultural setting. In our data set, we have 19 categories, cultural categories. Out of them, 13 are cultural categories, and 6 of them are generic categories. We also try to ensure that the benchmark ensures equal proportion of the data set. So that is something we started with. And the pie chart in the center, that's after filtering, that's the equal proportion of data set that we were left with. And then we also formally introduce some definitions of these domains that is pretty useful when you construct the question answer pairs later on in our process. Here you can see the scope of the dataset. It's 100 languages, 24 language scripts, 15 language families, and then the variety forces models to reason across different linguistic and cultural structures. That ranges from Swahili to Sinhala to Arabic to Urdu to Hindi. Now let's take a look at the data curation pipeline in our work that we follow. Our pipeline mainly comprises of two parts. One is the generic question answers, and one is the cultural specific question answer. To source the journal visual question answer pairs, VQA pairs, we use an open source Lava Bench wild dataset that comprises of 6 categories: indoor, outdoor, food items, memes, paintings, and sketch. We take that dataset, pass it on to GPT-4o, and we translate them into 100 languages. So here, the questions and the number of images and the images are itself same across languages. Once it's translated, we pass it on for a human verification and translation step, where we have the native speakers manually verify these samples. This gives us a total of 6,000 journal VQA pairs. Now, the second part of the data pipeline, which is actually the heart of the project, is the cultural curation of the dataset. To start with, we begin with automated image retrieval using tools like web scraping and Google search engine. We construct a country language pair and then pass it across to a search query. For example, a particular language X, cultural category Y in a country Z. And to ensure the privacy concerns, we only sample from open licenses like CC by NC and so on, and then public domains, so that we don't exploit these privacy concerns. There's one example in this table, for example, language Africans, cultural domain religion, and the country South Africa. So we make these unique pairs for the language and country, and then we append the cultural domain to it. This acts like a query. When we search for relevant images, this is how we're going to get it. Using this image retrieval process, we finally retrieve images across 13 categories. And we also provide these definitions, which we showed in the earlier slides. That is pretty useful when we're extracting that. Now, the next step requires this manual filtration. And to begin with manual filtration, we manually filter out all the relevant cultural images that did not mention the definition that we showed in the previous slide, or it didn't match with the cultural aspect of a particular language or a particular country. We also blur out personal identifying information such as face, watermarks, and so on. And then while retrieval of these images, when we were web scraping that, we also retrieve some of the additional metadata along with the image. This usually includes like image title, image captions, and so on. And this is pretty useful when we are generating the question answer pairs. So to ensure that the question answer is not completely synthetic, it's grounded with some realistic captions. The next part of that, once the filtration is done, we move to this generation of cultural question answer pairs. And to begin that, what we do is we pass this image, this added caption, which is called the metadata, and the language, cultural category, and the country to this GPT-4o that we use in our pipeline. And then we pass it on with this prompt template. And note that this prompt template is right now in English. So the question answers pair that we're going to get initially is in English language. And then later we translate them into this language. So data samples are unique per language. This is what I want to make sure, that unlike this generic part where the question answer pairs were similar, it was just a translated version. Here, the images and the question answer pairs are not shared across languages. That ensures that we have respective cultural aspect images, and they are pretty unique across the category. And then following this prompt, we just translate them into this native languages. GPT-4 does that for us. That's pretty standard. And then this is where the human verification and translation correction comes in, and this is pretty important part. For human verification step, we host a gradient-based inference along with some guidelines to the human annotators. The annotators were asked to see the question's relevance or not. If the question is something that cannot be answered using a VLM, such as if the question is only like, where is UCF located? So you don't need a VLM to answer that. A text-only model should be able to answer that. So now that's the image relevance is not there. So in this cases, we just rewrite those questions again that we got from the GPT-4o. So now the question is, where is this place shown in the image located? So now the VLM has to infer to the image. This avoids text-only bias that we usually see in the research literatures. And then we also ask them to do this translation verification. If they think that the translation of the question answer is incorrect, we ask them to identify the question, identify the translation error, and then we ask them to rewrite with the correct one. To begin with, we ask them to classify into 4 of the translation errors, for example, semantic error, culture error, language error, and grammatical error. We give them the definition of that. And then this is a chart where we summarizes the number of mistakes performed by or given by GPT-4o. And surprisingly, as you can see, that GPT-4o, when doing the translation job, it does more semantic errors as compared to a language error or cultural error, which you might expect. And then on the right, we do have some qualitative examples where the original language, the original question answer pairs in different language families, and different language scripts were not initially correct. So the human verifier had to rewrite those samples again and then just write them, make sure they are natively grounded and culturally grounded as well. For evaluation setup, we evaluate each question on different criteria and different evaluation prompts. For instance, MCQ is evaluated on accuracy. True false is evaluated on accuracy. But for short questions, we use correctness as a criteria, and for long question, we use consistency, fluency, and relevance. We again use GPT-4 as a judge here, and then different prompts are used for different of them. The scoring criteria, for again, we employ GPT as a judge, and GPT is responsible to score each sample between 0 to 10, and then it compares the ground truth with the predicted answer. And the results are completely verified by the native speakers. And this is the prompt that we use. And then the goal is that the GPT output should be as close to the humanly verified experts. If they're not, human verifiers would just manually solve them. And they would also classify them what was the error mistakes that GPT did in its evaluation. And then we also report that in the next slides. This is the overall high-level result across all the languages and across all the models we evaluated. To look at it more closely, on x-axis we have all the languages, and on the y-axis we have all the models that we evaluate. And then individual cells represent the average performance across 100 languages, or the average performance across all question types for a particular language. And the intensity of the cell indicates if the performance was super high, the color would be pretty high, and then the intensity would be lower if the performance was pretty lower. And then we evaluate this two closed source models, which is GPT and Gemini, and 14 open source models. So several analyses we were able to get out of this benchmark and the evaluation. First is this closed source models, for example, this GPT-4o and Gemini, they perform higher than the closed open source models. I think this claim is also pretty common and it's been well explored, and our studies also validate that claim. The best open source models that came out to be for our research was this GLM-4V, 9 billion parameters, and then the best open source models was this GPT-4o, which is 78%. But you can also see that the gap between the highest open source and the highest closed source models is pretty huge, it's significant. So we wanted to highlight that the difference between the open source and closed source when it comes to multicultural, multilingual grounding. But there were some common observations that both the open source and closed source models just struggle with some lower source languages like Amharic, Burmese, Sanskrit, and Kinyarwanda, and some other lower source languages. We also showed the performance across language scripts, and then we picked the best closed source models with the GPT-4o, and then we studied this Qwen2VL model, which was pretty famous at that time in terms of multilingual, because they claim to incorporate a lot of multilingual data in the training pipelines. But again, like we see for studying language scrapes like Geese, which is an Amharic, and then Sinhalese, which is a Sinhala, which consists of Sinhala language, and Odia, and such as Odia language, or maybe Myanmar, Burmese. They have this lower performance, and then the models struggle on them. But at the same time, certain language scripts, which are predominant, for example, this Chinese script or Cyrillic script, and then this Latin scripts, which has a high number of languages, they seem to perform consistently well. So one observation we wanted to exploit here or find out here is if a certain language script has more than one language script, more than languages in it, it could also indicate that the presence of one language, which is pretty high dominant in the language training pipeline, is also supporting other languages in the same particular script. And this is a common trend that we got looking at the Chinese, Cyrillic, or the Latin language script. Error analysis on the language scripts. This is what we're talking about when the GPT tries to evaluate them, and then there are some errors in its actual evaluation, which the human speakers and human verifiers are supposed to fix them. So the first error is the lack of knowledge. That means the model is not able to answer the question. It fails to identify a correct answer for that. Then the second is lack of cultural understanding. Then the model does not understand the cultural aspect properly. We'll see an example in a few slides. And then there could be a language error where the model does not output in a correct language semantics. For example, it mixes certain languages, or it doesn't write the proper word correctly that it should. Or there could be reasoning errors. That means the reason the model gave is not correct, or the translation errors. For example, the few native words were not properly used or not properly translated. And the other is the perceptual error. This is something that we introduced where the model fails to identify the placement of a particular object when in an image when prompted with a multilingual question answer. And then we also show some results, which is a pie chart of human verification on top of the error analysis and across different language scripts, such as Bengali, Sinhalese, and then Russian and the Portuguese. And as we can see that there is no common trend across these language scripts and languages. For example, this Bengali seems to struggle in cultural understanding and lack of knowledge, but the Sinhala struggles on lack of knowledge and language error more. But Russian scripts, they struggle with lack of knowledge. And then Portuguese. So there is no common trend across different languages. That means different languages needs different presence in the training data, and they would need the modifications. So just having a translation of the training data and then training combinedly and jointly is not going to be enough in the training. We also show some qualitative examples of error analysis on the scripts. So on top, we show some correct results that is output by GPT. That means that GPT was able to get or capture the correct output, and it gives you the score. And if the score is pretty high, we mark it as a correct response. And then we also show some incorrect responses where the output, the predicted answer is not correct. And then we also write what is the reason for the error, like we showed in the previous slides. If we look at it more closely for this particular question answer type, here the question asks about the religious festival that is being celebrated in the image. The model in this case, which is GPT-4o, it responds that it's a religious event. However, it struggles to identify which is the correct one. It struggles to differentiate between the theme of the religious event, where the predicted festival, in this case, is the prophet's birthday, which usually has a green theme in a mosque. And then the dressing of the people that are shown in the image, it doesn't seem to be a cultural dressing. It's not a cultural attire. So the model confuses between that. So although some parts of the answers are correct, but it does not understand still fully the correctness. Then we show some results on the language family. We club those results across language families. And then again, on GPT-4o and the Quantuvia, we identified that there are some language families, for example, this African Congo, which has Igbo, and then Kinyarwanda, and then Swahili, Yoruba. These particular language families, they kind of struggle. And then for GPT-4o, anything less than 80% seems to be struggling. And then we can see the performance goes down as low as 65, 70% on some language families. In Quen, there's like a big difference when it comes to a very lower source language families and higher source language family. So there are 15 language families in total and 24 language scripts that we showed in our work. Another interesting work was the question types that we have in our paper. Like we showed different question types, including multiple choice, true, false, short, and long questions. So we showed the performance distribution across a couple of models, including closed source and open source. So there is an interesting trend. The closed source models, they perform better on long visual question answers. The open source models performs better on the short visual question answers. And they both fare slightly better on the decision-making questions. And one of the reasons is since it's just one of two options in true false, so the randomness is 50%, and for multiple choice question, the randomness is 25% given for options. And then the one hypothesis that we assume that why open source models performs worse on this long question is because these closed source models, they are trained with a lot of reinforcement learning with human feedback and other tools to make it sound like fluent and coherent, and it gives the responses like very close to the human. So that's why it's performed pretty high on the long questions. And on the right, we show some cultural category results across these different models. So these are the 13 categories we have in our paper. And then the few things to know about is the closer model like GPT-4, it outperforms with 80.3% on average, but GPT-4 achieves like a various range of accuracies. It achieves maybe 83.7% on education and heritage, but it drops down all the way to 72.7% on notable key figure category. So that means there are certain categories that's not fully aware of, and that still needs to be explored, and then it needs to be added into the training data. And then other categories, such as notable key figures and customs, they're often cultural specific and underrepresented in the training data sets. So that's another reason why the performance of them is quite struggling. Now, in this ablation, what we try to do is, when prompting a model, to answer a question, particular question, we try to add some country level information in the prompts for multimodal evaluation. So if a question is, if there was an Urdu question, we would add a country name that this particular sample is taken from X country, which in that case would be Pakistan and India and so on, right? And we see that these models like closed-source model like GPT and Gemini, they try to make some good use out of that extra information. They better utilize the added geographical context. But this open source models, they also perform slightly better, but they don't utilize this information as much as the closed source models. And then we talk about this annotated demographics for our work. Over 60 volunteers participated for the research project, and the volunteers came from 50 plus countries. The 1/4 of the presence of the female volunteers were there, and then approximately 46% fall in this 18 to 25 page limit. Approximately 80% or higher speakers were either native speakers or bilingual. That really validates our claim when we mentioned that it's humanly counted and humanly verified. And then over 87.9% of the annotators, they actually lived in the country from which the culture examples were drawn from. Some qualitative examples of our paper, again, like in this case, which is Chinese Simplify across a category of lifestyle. And then we show several question answer pairs, including multiple choice question answers, long questions, true, false, and short question. So to summarize, we have one image. We blur out any faces, which is not notable key figures. For notable key figures, we actually keep those faces just to make sure that the model understands. But for privacy, we blur out the rest of the personal identifying informations. And then for every image and a particular cultural category, we generate 2 multiple choice questions, 2 short questions, 1 true, false, and 1 long questions initially. But again, if the questions are irrelevant or completely culturally off, then it has to be like either discarded or rewritten by the human annotators completely. Like another example for Italian category music, and then we show some again examples on that. Now we move on to the next work, which is the same culturally aware multilingual, but in this case, a video large multimodal benchmark. For that, we present our paper, a culturally diverse multilingual video benchmark and model. This paper is accepted at ALM-Bench 2025, and this will be presented next month in China. So the problem with the current video large multimodal models is, in the case of images large multimodal models, like image VLMs, we saw there are some existing works and benchmarks that target the multilinguality. But in this case, most of the existing works are English-centric only. They struggle with cultural and linguistic inclusivity, and they also struggle on lower source languages, for example, Sinhala and Tamil, like we saw. Also, the problem is there are not any particular models that are specialized for large multimodal in case of videos. However, if the baseline LM is multilingual, they still have some inherent multilingual capabilities, but specifically the training data of VLMs, that's not completely focused on multilingual. And especially, we didn't have any benchmarks or any works that targets to capture that. Like we see some existing work, we try to come up with some existing literature review, but we couldn't find anything that's multilingual focused. A lot of these works are focused on certain domains, certain tasks, and then total number of samples they would have. Sometimes it would be super high, but that would be simply auto-generated or human-generated. And then the question types they would have is multiple choice questions and sometimes open-ended as well. And then they would have a certain number of total videos and so on. And then before starting, we also show some qualitative examples where GPT-4 models, which is supposed to be good, they struggle on these lower source languages. Like in this case, where Sinhali scripts or the Urdu scripts, when given a question answer, it tries to predict an option, and then we also generate the reasoning along with it. And then the error type seems to be lack of cultural understanding. So to complement this, we propose ViMUL, which is what we call multimodal vision language video LM. And then this work comprises of 14 languages. It's again comprises of lower source plus higher source languages. It comprises of 15 domains, and total number of samples are close to 8,000. And then we have rich question types, including multiple choice and open-ended. And then the annotation type is rounded with both automatic annotations and human annotations. So this is the language distribution samples we have. But in this case, we have more presence of English because we took some benchmarks from English and then we translate them into multilingual for gender categories and culture categories again. So that's why we have more presence of English as compared to other benchmarks. But again, the rest of the language seems to be pretty consistent, about 6 to 7%. And then we also mentioned these 10 cultural categories we have. Some of them are drawn from our ALM-Bench paper, but some of them are also drawn from other inspirations. So in this case, we have lifestyles and commons and festivals and foods and cuisines, sports and so on. But all of them have like pretty equal proportion of 11 to 12% in total. To quickly summarize our pipeline that we use for the data curation, it also involves general question answer pairs. As you can see on the right side, we take existing data set that we translate that using GPT-4o, and this translation we QA pairs in 14 languages that is passed through this human verification by native speakers. And then this generic VQ pair that becomes part of the data set. So the generic questions, we have close to 5,000 questions. And then for cultural questions, we start with something different. Since we want to look for these videos and manually curate these videos and gather these videos, what we do is we pass on a query to ChatGPT or GPT-4o, where we ask it to give samples of a particular category from a particular country, right? So again, we have this concept of language country pairs, and we try to leverage that and find what are the famous, let's say, what are the popular sports categories in a particular country X. And then it gives us like a list of topics and sequences that we can initially scrape from. And then when it does that, we use that to manually search this video. So the video collection process is manual, as we have to look up all these videos, and we have to make sure that it passes some criteria, that it has to be longer than a particular time duration, or it has to be open license, the resolution has to match, and then whether it has audio or not, or whether it has subtitles or not. So those were some decisions that we took place. Although we did not use audio as a modality in our evaluations, but we just wanted to see if it's actually capturing the multilingual aspect that we want the video to capture or not. Sometimes the video would be in English, but sometimes the caption would be in a different language. So that wouldn't suffice, right? We want it to be actually multilingual to have the highest quality of data that we could possible. We gather these videos across these different categories like we see in this center. And then the question answer generation in this case was completely manual. We have these human volunteers with us that we went through each of these videos and generated some question answer pairs, including multiple choice and open-ended questions manually. And then after verification of them and after their curation, which is of highest quality because we don't start from GPT-4 in this case, we get this cultural wiki pairs for foreign language, and that becomes a part of the data set again. The cultural pairs are a little less than like generic here, because in terms of videos, it's not possible to manually use or just web scrape a lot of videos because it has to be manually watched. And some of the videos are actually, because we divide our work in 3 video categories: short videos, long video, medium videos, and long videos. Short videos would be anywhere between less than a minute or a few seconds, and then the long videos could be as high as like more than 4 minutes, more than 10 minutes. So that would be pretty hard to watch. And then again, curation of this question types would also take a lot of time. So along with the data set, we also felt the need that, okay, since we don't see any work that's primarily focused on this multilingual video VLM, so we come up and train this, we call it as a baseline model. But what we initially did was we took this Lava 1 vision model, and then we created this 1.2 million samples question answer pairs. And that consists of existing English video translations or English video instruction datasets, question answer datasets, and we translate them into non-English languages like the rest of the 13 languages. We use datasets such as Video Instruct 100K or Lava Video 178K, NextQA, Perception Test, Clever, and etc. That was primarily focused on English data before translations. And then after translation, we manually sample like a subset of 5K, 2K, 10K samples, and then we try to humanly validate that. But since we know that, okay, sampling maybe even if it's sample 1,000 samples, it would take a lot of human efforts and super expensive. So to complement it, we did something called as cycle consistency, where we took, let's say, 20K question answer pairs, and then we translate them back to an English again, and then we use Qwen3 model, the bigger gradient, to compare the actual ground truth English question answer into the compare one. And if it's above certain threshold, we keep them, or if it's not, we just discard them, or we just redo it. So once we have the certain threshold and the quality that we needed, because since there's 1.2 million samples, it's humanly impossible to validate each of these question samples. So our benchmark was humanly verified and culture verified. But for this, we employ several techniques. We manually verify a subset of it, but for the rest, we did cycle consistency and back translation checks to ensure that the translated QA pairs are of sufficient quality. We again put like a lot of summaries in it, but just to summarize a little few and we'll take question answers after that. But we show the performance of open source versus closed source comparisons, where we see that, okay, this closed source model to perform significantly higher, and then our trained model, which is a ViMUL, it performs better than the baseline model, which is Love Vision. Although the improvement is not substantial, but what we see is that it kind of complemented the lower source language such as Tamil, Urdu, and so on. We actually got a better performance at the baseline model Love Vision. But for high source language, we see that the performance seems to be a little drop, and that was because that could be possibly because of a lot of reasons, and one of them could be the training scale that we chose and the training scale that actual One Vision was trained on. There is substantial difference. So this is a baseline model. We don't claim to be the soda in multilingual settings, but we seem to have like a better performance than the closest ones we have. And the other models like Vila and Video Chat GPT, as you can see, they were pretty popular back then, but the performance that's crossed like 30% benchmark, which is a little surprising. And then on the right, we show some like these same models again, and then we show their performance on different categories, cultural categories and gender categories, and there's like the entire range of performance that we're getting. For example, the models like Law One Vision, they perform super high on sports, and then notable key figures in media entertainment, but they drop the performance down when it comes to art and literature. But when we train our ViMUL model, they kind of substitute the performance, and then that has higher performance. And then we have some other analysis in our paper as well. We also we compare with the image benchmarks, like what if we take, instead of an entire video, we take a particular sample frame. Would that suffice? That would mean that we don't need a video benchmark. We just have a video, you just take a random frame, and then that should work. It was suggested by one of the reviewer, but it didn't work out because we showed a random frame, initial frame, the last frame, but we saw that the temporal consistency is not captured in the image LMMs. So that kind of validates the need of the video benchmark we have. These the archive links and then the GitHub project links for them are here, and then if you want, you can look at them and download the data set and give us feedback if there's something we can build on top of it. That's pretty much it from my side. Thank you so much for listening. Just me if you want to connect with me, and then like to take any questions if you have.
Thank you so much, Ashmal, for the great talk. If anyone has any question, feel free to unmute. I'll start by asking that, how did you choose these 100 languages? Did you have any criteria for including or not including any language?
Right, so we initially wanted to take 200 languages. That was on the basis of this no language left behind Microsoft paper. That was a machine translation engine. That was done on 200 languages. But initially, the major bottleneck of this project is getting this human annotators that can actually verify those languages. It's not just expensive, it's sometimes impossible to find. So when we're looking at this crowdsourcing platforms like Mechanical Turk and Fiverr to hire those annotators, we wouldn't find for a lot of languages, we couldn't just find these annotators. They're just scarce. And then again, after finding, if we had the annotators, the training data that's available or the internet, it's available on the internet, it's not again super high. So to ensure that we have to have like a higher quality, we have to trim down and filter out to 100 languages. So we started with way higher, and then based on the annotators and so on, we just decided to go what we have the best.
Right. And do you think that if there's this shortage of annotators and we have unlabeled data, then maybe there should be some sort of work that is focused on unsupervised learning or self-supervised that can leverage this unlabeled data for multilingual, multicultural in a self-supervised way without annotators.
That would be interesting to find again. Like we said, there are some machine translation engines that were pretty popular in the start of Transformer era. But we did start with this MT engines before using GPT-4 as a translation engine. We used this no language left behind MT, and then we translate some of our data sets and we check the performance. And the performance are not just as good as these closed source models or proprietary models. So the idea of self-supervised learning, I don't think like they're particularly exist like a VLM or I know there are some LMs in this case that's been trained on very large number of languages, but on such a scale, the presence seems to be pretty scarce, and still the community seems to be working. Even for our case, we were actively looking for volunteers in a lot of different groups, and I was also looking at Korea's group. I posted a lot of times, and then IA groups and so on, like to find these annotators and to get them, even for weekly supervised or self-supervised. Um, I don't know. It would be interesting. I think it's an interesting direction that to have it, but still you need some at least a small amount of label data to maybe move to unsupervised or weekly supervised.
Right. Thanks.
Also, if anybody is curious on the future directions, we also applied a similar task to text-to-image model, where we wanted to study how the multilingual grammatical variance applies this generation models, stable diffusions, and so on. And that is also a part of MNLP findings that will be presented next month. So I thought of putting it in the presentation, but I just kind of kept it separate. So like there's a lot of future directions that could be taken in that.
So if we don't have any other question, we can conclude the session here. Thank you so much, Ashmal, for the amazing talk and great work.
No problem. Appreciate it.
Yeah. Thank you so much. Take care. Oh, I guess we have a question.
Sure.
You can unmute and ask.
Yes, thank you. It was a great paper. So basically, I was working on a project. It's not related to your project, but I was just want to know that if I want to train a model to adapt something like a conversation between two persons, like if I'm talking to someone. So how do you decide if that the model is capable of doing that? Like I am just creating a twin of mine, which I can use if I am not present any at any moment, and someone and want to interact me urgently. So if they want to adapt my tune of how I talk based on some scenarios, so can you give some idea on that? Because I'm not able to make my model to adapt my talking, like the way I talk, the way I type, the way I text.
Okay, so is it in the textual form or is it in the form of audio that you have to
Uh,
code?
it's it's based on text form.
Okay, and like what is the training data set size that you have that you want to adapt it to?
I was training on my WhatsApp chats. Basically, I just used GPT and DeepSeek to generate some text based on the input I give prompt. But it was not adapting that or what I expected. But it was just doing prompt only, like what an LLMs usually do. So, if you can give me some ideas, like how can I improve that?
Right, and was it bilingual or English language only, or
It was only English now. I was just using English language now.
okay? To begin with, did you try giving like a few short examples or um,
Yes, so basically, what I did was I give a brief history. Like there are two persons, Alice and Bob. So they have a brief conversation in between, which I give them, and then I try to use Gemini 2.5 plus to train on. Then I switch off like I transform, like I switch off the Alice as a human. I switch on his twin, and then I ask Bob to ask Alice twin, like what how was your day going and how your project was going. So instead of giving a straightforward answer like okay my project was going well but my manager has some, because I mentioned in my previous prompt that Alice was working on a project and her manager is asking her to increase the accuracy and like that. But the twin of Alice was giving response like, yes, the day was good, but something like that, and it was not giving the accurate answers which I expected.
Okay, I think there are a few things that you can try with the prompt engineering thing. Like, unless you want to go to some training approach where you want to have like a small lower adapter and just train it on a few iterations and see if it's adapting for any open source.
Yes.
But you can just like leverage this pre-training like prompt engineering approaches. For example, just make it a more harsh, or like, okay, maybe have like two LLMs talk to each other, where one is generating the response, like as in Alice and Bob, and the second one is giving feedback on top of it. And then if it feels like the tone matches the actual speech or example that you give, it just let it go. And then if not, then it just ask it or append it to add certain words where it's not just enough. So something um, like LM Arena Play, where you can just um, fit in two LMs or VLMs against each other, and then it's just giving constant feedback, and that feedback is appended in the context history, and then with the next time it's generating, it tries to give something that is inclusive of that. So you could try something like that.
Okay. Thank you.
You're welcome.
All right. Thank you, everyone. We can conclude the session here. Thanks, Ashmal. Take care, everyone. Bye.